HVAC 13, why can you assume that the total pressures equal each other? This problem was about a branch takeoff in a duct. So really kind of just a very typical situation where you have a duct main coming and there's a branch and it continues on. So we could say this is 1, this is 2, this is 3, this is the flow. Some goes this way. Most of it continues on. And the question is, why can you assume that the total pressures equal each other? This is really a fundamental principle of I guess duct design, but more generally than that, it's the conservation of energy is really what it comes down to. Or if you want to be more fluids oriented in thinking about it, you can think about it as Bernoulli's equation. What does Bernoulli's equation tell us? It tells us that the total pressure in general is equal to three things, the sum of three things: static pressure, velocity pressure, and pressure that's attributable to elevation. You can write this in a number of different ways, but this is one way of writing it. And that assumes that there's no losses. If there are losses, we need maybe another term there. And when it comes to ducts, everything's more or less horizontal, or if there is a change in elevation, it's probably not significant enough to be a major contribution to the total pressure. So this term can be ignored. The total pressure is just an interplay between these other two parameters, static pressure and velocity pressure. So a lot of times HVAC engineers won't write it this way because they're not really thinking about it as Bernoulli's equation. They're just thinking about it as duct work. So they'll write it this way: TP, total pressure, equals SP, static pressure, plus VP, velocity pressure. And that's preferable. It's a preferable way to think about it for HVAC engineers that are just, I don't want to say simplistic, but it's a narrow view of the world. They're just thinking about duct work. They're not thinking about, Newton's energy balance or even the wide range of things that you could do with Bernoulli's equation. Once you get to that idea, that is an extremely useful thing for analyzing ductwork. The total pressure in all three of these states is the same at 1, 2, and 3. Very, very good thing to know. And you can think about it just conceptually without even throwing any numbers at it. Imagine you have some total pressure at 1, and that pressure is a mixture of some amount of static pressure and velocity pressure. The velocity pressure is what's making the air move down the duct, to the right in this case. And the static pressure, you can think of it as the pressure that overcomes friction or allows or kind of pushes against the walls of the duct. It pushes perpendicularly to the flow. It doesn't actually drive movement, but it's like if you blow air into a balloon and seal it off and just hold it still, the air's not moving. Well, the air molecules are always moving, but there's no like bulk velocity. It's just kind of moving in place. But there's static pressure. It's pushing against the walls of the balloon. Otherwise, the balloon would collapse on itself. But it's that static pressure that's pushing outward. That's true in a duct too, or in a supply plenum that's fixed. There's just this buildup of static pressure, even if there's not very much velocity. Okay, so there's a mixture of both at all points. And then when we get to 2, what happens? Well, some of the volume has branched off, so there's less volume now. And we know that because Q equals VA, continuity law, that if there's less volume and the area hasn't changed, which isn't necessarily the case. Sometimes they make ducts get smaller as you go along for good reason. But let's just say that this main trunk is going to stay the same area at 1 and at 2. So if there's less volume, then there's going to be less velocity. So the velocity pressure at 2 is going to be lower than the velocity pressure at 1. But the total pressure has to be the same. So that means the static pressure has to be correspondingly higher, such that their sum is the same. And then at state 3, this branch is smaller. I guess it depends how much volume actually went through it. But when you go down a branch, you want to speed the air up, so it takes this new direction. So typically the velocity pressure would be higher and the static pressure would be lower. But, every problem's different, so deal with the specific numbers that are given in a problem. But conceptually, this is something like this is a nice that you can just store in your brain and be ready to use for duct problems.